So today we are going to discuss a very important and very popular proof. The proof of that is root over 2 is irrational, or for that matter any number, any square root is irrational. How do we prove that? Let's first understand what is an irrational number. Irrational number itself means no ratio. Irrational means having no ratio. No ratio means that we cannot express that particular number as a ratio of two numbers. For example, pi is 3.14159 and it goes on and on up till infinity, and we cannot express pi as a ratio of two numbers. Although there is this ratio that is 22/7, but 22/7 is just an approximation. It is not the actual ratio. The actual numbers are these numbers. Okay, so what do we understand is that irrational numbers, they don't have any ratio. Irrational number, these numbers, after the decimal points, they just gonna never end. They go up until infinity. They never ends. And the third number is that they never repeat itself. You see, these numbers are not repetitive. They are all unique, all different, so they never repeat. So therefore these kind of numbers are called irrational numbers. Now, how do we prove that root over 2 is irrational? Let's try and prove that root over 2 is rational. Rational means that square root over 2 is a ratio of two numbers. So we are going to prove it by contradiction. So let's assume that square root of 2 is a ratio of two numbers, that is a over b. So we can write that 2 is equals a square over b square. And similarly, we can write that a square equals 2 times b square. Now we know from the fundamental theorem of arithmetic that every number, all of whose prime factors has an even exponential, all of whose prime factors have an even power, are perfect square. For example, as we have taken here as 225 equals 3 squared times 5 squared. So you see that when 225 is broken down into its prime factors, so all of the prime factors, here we have 3 and 5, all of the prime factors have an even power. Let's take another number, that is 64. If you break down 64, so 64 can be broken down as 8 times 8. Since 8 is not a prime factor, so we can break it down even more and we can reach here 2 cube times 2 cube. And therefore we have 2 power 6. So you see that 64 is 2 power 6. Similarly, 225 is 3 squared times 5 squared. So you see that 225 is a perfect square because all of its prime factors have even powers. 64 is a perfect square because all of its prime factors have even power. So this is the fundamental theorem of arithmetic. Now when we compare the same thing to b square, now the prime factors of b square must also have its exponents, its powers, as even, right? In case of b square, all of the prime factors of b square must also have its powers as even. So let's assume that some power may be 2 power 2m, some other power may be 3 power 4q, next maybe 5 power 6m, and so on and so forth. Okay, now what do you think that the exponents of 2b square, if I multiply 2 with the b square, what do you think that 2b square, all the powers of the prime factors of 2b square will be even or not? So in this case, when we see that they will not be even, because 2b square is 2 to the power 2m plus 1, 3 power 4q and 5 power 6m or whatever. So then you see that 2b square is not a perfect square. is not a perfect square, because definitely one of the power will be odd, and the requirement for a number to be a perfect square is that all of its prime factors must have an even power. So we have seen that 2b square is not a perfect square. Is not a square because 2b square, all of the exponents do not have any even power. But then if you see on the other hand the a square, if a is a square, then all of the prime factorization must have an even power for a square. But then if a square is equal to 2b square, so then not all of the prime factors must have an even power. So therefore this gives us a contradiction. We can write here that powers for a squares are even, while power for 2b squares are odd, and an even power cannot be an odd power both at the same time, and this gives us a contradiction. So therefore our assumption that root over 2 is equal to a over b is wrong. So therefore we understood that square root over 2 cannot be expressed as a ratio of two numbers. Now this same logic can be used to express other problems. If you need to prove square root over 3 is irrational, or some might need to prove square root of 7 is irrational, then how do we do that? We take it as the same way. We take that square root over 3 is a over b, and then we can write that 3 equals a square over b squared, and then we write a square equals 3 times b squared. And now exactly the same thing, you put out the same argument that prime factors of b square have an even power, but then all the prime factors of 3b square are not even. Similarly, in case of a square, it must be even. The power of all the prime factors must be even, but then it cannot be even and odd both at the same time. Similarly, you can also show it for 7, root over 7, or you can show it also for root over 11 and other things.